So get out that periodic table that has this reduction chart on the back of it. Okay, so this is going to become your friend. So this reduction chart is going to be part of what's going to happen with this lab. So let me kind of begin to paint the picture of this chart in order to kind of look at extremes. Okay, so if you look up at the top, you have F2 plus 2 electrons turning into 2F minus, and over here you have a number. That's 2.87. Okay? Now, in contrast to that, way down at the bottom, you have a lithium ion trying to gain an electron, turning into elemental lithium, and that has a value of negative 3.05. So this chart right here, okay, number one is measured in volts. Okay? So volts is a measure of what we call energy per coulomb. So you can also express that as joules, which is energy. Okay, that's the universal thing in all of science, is energy in joules. And then you have per coulomb. Okay, per coulomb is the amount of charge that there exists. So, for example, and do not worry about this number. You don't need to know this number. I'm just giving you this number for reference. If you have a single Chihuahua or St. Bernard, that has a charge of 1.60 times 10 to the negative 19th coulomb. Okay? So every electron that we've ever looked at has the exact same mass and the exact same amount of charge. Okay? But they're tiny. They're little Chihuahuas. So once we figured out the protons, the St. Bernards, we figured out, even though they're much more massive, like it takes about 1,800 electrons to balance out the mass of one proton, that proton has the exact same amount of charge as that electron does, even though it's much more massive. So charge is independent of mass. So when you look at these numbers, okay, and we're going to spend a lot more talking about what these numbers mean, but here's what I want you to get for now, is that the more positive that number is, the more likely it is to go in that direction. So what that means is that fluorine, elemental fluorine gas, really wants to take in electrons and turn into the ion, okay? Because it has this big positive number. So it really wants to go in that direction. Now, in contrast to that, you have lithium. You have a lithium ion way down there at the bottom. And lithium's going like, dude, I don't want that electron back. No, okay? We can make it take it. We can make elemental lithium, but it's not happy, okay? It's like, hey, you got to take your little brother Timmy with you out on the date tonight. No, okay? Your parents are going to have to force you to take Timmy. And given the first chance, you're going to ditch Timmy. Okay, what happened to Timmy? Don't know. We were at the zoo and Timmy's not gone. So here's the point. The farther up you are, the more it wants to go in this direction. The farther down you are, the more it actually wants to get reversed. Now, so we're going to look at a trend. Okay? So I'm going to show you two ways that you can see the trend. How you pick to remember this, purely up to you. So we're going to look at what we did yesterday. So yesterday, we took hydrochloric acid, which was those hydronium ions. We put that in the presence of magnesium. We formed magnesium ions and hydrogen gas. Okay? That's what we did. So that was the nuts and bolts of the reaction that we did yesterday. Chlorine was there, but it was Taylor Swift. It was just watching, didn't care. Now, so if you notice kind of right here in the middle, you have two hydrogens plus 2 electrons. You're forming hydrogen gas, and that has the value of 0. So hydrogen is like the reference point. Okay? We arbitrarily define that as being 0, and then we judge all the other values relative to that. So here's what's important. And this sounds a little bit biblical. The way this happened with the hydrogen, it goes as it is written on the reduction chart. Because the hydrogen gained 2 electrons, and it turned into H2. So it went in the direction of this. Remember, and remember this from the lab. This is a reduction chart. It's not an oxidation chart, reduction chart. Okay? Which means everything written goes as a reduction reaction. Now, if you look down here, if you go down below hydrogen, you can find magnesium way down here. Okay? So magnesium's way down here. But, and you remember this from the lab today, we did not start with magnesium ions. Okay? This is important. There's magnesium, and then there's magnesium ions. We started with the elemental form of magnesium. Okay? So what happened is that the magnesium turned into Mg2 plus 2 electrons. That's what happened with the magnesium. So did the magnesium get oxidized or reduced? It got oxidized because of the fact that basically the proton came along and says, hey, spare the proton, spare an electron. Magnesium goes, you're going to take them. As a matter of fact, take 2. It's buy one, get one free special day. Okay? So I really don't like either one of them. They've been a pain since we formed in the star 1,000 years ago. So, you got this going on, right? So, some people like to think of this as called the over-under game. So, if hydrogen is over anything below it, hydrogen will go in this direction, and the magnesium will get in the reverse direction. So if I put anything below hydrogen, this is why it's called the over-under game. So if you look at hydrogen gas, okay, right there in the middle, 0. So if I take anything that's below that, that's on the right side, that's a product, okay, like magnesium, aluminum, silver, any of those below that, that hydrogen will steal an electron away from it. So hydrogen will be reduced and it will oxidize anything that's below that. That's why it's called the over-under game. Okay? So if you like the over-under game and you can have one reaction that you can have straight in your mind, say, okay, great, what happened? I know if I take magnesium and drop that in hydrogen, hydrochloric acid, I get a reaction. Where's hydrogen? Where's magnesium? Oh, it's the over-under game. Okay? That's an option. Option number 2, more of a mathematical operation. So, as it is written, that's why I said this gets a little bit biblical. If you find the magnesium, as it is written, that has the standard reduction potential. That's what that column is called, the standard reduction potential. As it is written as negative 2.37 volts. Okay? What that means is that it really doesn't want to go in this direction. Okay? It really feels better going in the opposite direction. So, if it's negative written as a reduction value, if it becomes an oxidation value, it becomes positive. Now, if I take a positive, check my math, get this. If I take a positive 2.37 and add that to 0, I get a positive number. So here's the other way that you can look at this. If the reduction potentials, if you keep one as the reduction and make the other one the oxidation, and you add those together, and that's a positive number, that's what we call a spontaneous reaction that's going to take place. So if you like a mathematical approach, you have some reduction potential, okay, however that's written, and then you reverse what you think is going to be oxidized, and you add those numbers together, that works out to be a positive number, the reaction is spontaneous and it's going to take place. Now, in contrast to this, let's say that I take a piece of silver and I drop that into hydrochloric acid. What's going to happen? Play the over-under game. Where's silver in relation to hydrogen?
It's higher.
Higher.
So it's going to get reduced.
No, it's not.
So it's not going to get reduced.
Why?
It's above.
If you play the over-under game, silver is, why do you think we use silver in jewelry?
Because it doesn't go away.
Oh, it doesn't react.
Because it tarnishes.
Oh, well, that has some impurities in it. So if you look, silver up here, now again, this is silver, not silver ions. This is a chunk of silver. So if this happened, if you go up there, right, and you find silver Where's hydrogen?
Actually
Boom.
under.
Silver is up above that. Why am I blind today? Ah, there it is. Okay, that's 0.80. So if this happened, the silver would get switched, and that would be negative 0.8 plus 0. That's a negative value, last I checked. That means it would be not spontaneous. So elemental silver in hydrochloric acid, nothing's going to happen. Magnesium in hydrochloric acid, you're going to get a reaction. So you can either play the over-under game, or you can look at it mathematically. Okay? All right, so let's just talk about the 2 parts of the lab. So, first thing you're going to do is that you're going to do a total of 6 reactions. So, I've got stereo microscopes. They look like microscopes, but they're just for they're for seeing bigger things. So, you're going to take 2 small pieces of copper, put them on a watch glass, and you don't have to do this in this sequence. But you're going to put 2 small pieces of copper like this on a watch glass. Then you're going to take a dropper and you're going to add 2 things to it. You're going to add zinc nitrate, and then you're going to add lead nitrate. So I'm going to add zinc ions. This is going to be important. And I'm going to add lead ions. Okay? So you're going to add lead ions to copper, and you're going to add zinc ions to copper. And you're going to look and you're going to see if you get a reaction. If you get a reaction, it will be noticeable. Okay? So, the first reaction that you're going to do, and if you want to put in the nitrates, you can. If you just don't want to do the net ionics, that's what I would do because it saves you some time. So you're going to have zinc ions and copper, and you're going to have lead ions and copper. Okay? And are you going to get a reaction? You also need to make a chart that records observations. So you're going to have 3 different metals. You're going to have copper, you're going to have lead, and you're going to have zinc. And then you're going to react them with copper ions, zinc ions, and lead ions. Now, obviously, why didn't I tell you to put copper ions on copper? Nothing's going to happen. Okay? Copper is going to still copper. Okay? So then, like in this situation, you're going to take elemental copper, and you're going to react that with zinc ions and lead ions. Okay? What's going to happen? It's very possible that you don't get a reaction. Okay? That's cool, because sometimes non-reaction tells you just as much as if you get a reaction. So you're going to have this chart. Okay? And the reactions that happen are going to happen. You will see a reaction. That's a cool part of using the stereo microscope. So I'm going to have, do not push these, wash these down the sink. Okay? I'm going to have a container over there. I want you to put all of this from that wash glass into a container. Do not put these in the trash. Do not wash them down the sink. Okay? So then you're going to get a couple of pieces of lead. On the lead, you're going to add copper ions, and you're going to add zinc ions. Then you're going to take a couple of pieces of zinc, and onto the zinc, you're going to add copper ions, and you're going to add lead ions. Okay? 3 of these should make a reaction. 3 of them should. Okay? Not to bias you, but that's what it's done. Okay. So, that's going to be part 1. And everybody, there's 2 distinct parts of this. So I don't want everybody trying to do part 1 at the same time because it doesn't make any difference. The second part, you're going to take a pair of tweezers and you're going to take a few crystals of MnO4. And I mean like a few crystals. Okay? You take a pair of tweezers, boom. You're going to find the mass of a very small number of tweezers full of potassium permanganate ions. Dark purple. Do not get this stuff on your skin. As a matter of fact, this is one of the very few labs I'm going to tell you, you have to wear your safety glasses because you're dealing with concentrated sulfuric acid and potassium permanganate, both of which are very nasty to your eyeballs. Wear your safety glasses in this lab. So then, and I've given you the mass of potassium permanganate, it's there 158.04. You're going to add that in 10 milliliters of water. Notice that I did not write 10 milliliters, okay? Notice I put 10.00. That needs to be an exact measurement so that you can get an exact measure of that molarity. The second part, you're going to get about 6 crystals. This is about 6 crystals of ferrous ammonium sulfate. I've given you the molar mass of that. You're going to dissolve that in 5 milliliters of water. Then, to add 12 drops to the 1.5 molar H sulfuric acid, okay, there's going to be a dropper bottle. It's going to say 1.5 molar sulfuric acid. You're going to add that to the FeSO4 solution. So you can have the FeSO4 solution. You're going to add the sulfuric acid to that. This is where the hydronium ions are going to come from. Then you're going to add that mixture drop by drop to the solution that had the MnO4. It should turn clear. Okay? That's when you know it's gone from MnO4 into Mn2+. And that stuff you can just wash down the sink. So there's 2 distinct parts to this. The potassium permanganate and ferrous ammonium sulfate reactions, and then the other one. So basically I don't want everybody starting on part 1. And some groups starting on part 2, some groups starting on part 1. Ready, break, here we go.